Well, we made it through our first exam. Um, so we're through, I don't know what the first exam is really about. I guess it's an introduction to or rounds out some thermodynamic type stuff and rounds out some thermodynamic stuff and just introduces equilibria. Now we'll get on to, again, colligative properties. It's kind of a bunch of different stuff that's just kind of ham-fisted together. Now things will get a little bit more specific. So in this particular unit, we deal with acid-base chemistry. This is traditionally one of the more challenging pieces of the course for people, I think, just because it combines a whole bunch of different things. So let's wade into it today. So let's see. So first we can just start. So there's a few different ways that you can define an acid and base. So we're just looking at acids and bases right now. Hopefully you've had some exposure to acids and bases. The most common and the most useful definition, and the one that we'll mostly stick with, is the Bronsted-Lowry definition, which is just that acids we'll call acids proton donors. We'll call bases proton acceptors. The other definition that's useful is so this is the Bronsted. We'll just call it Bronsted. So just real quick, like what that would look like if you're looking at like let's say you have HCl and you're reacting it with sodium hydroxide. Actually, let's react it with ammonia. So let's say you're reacting these two molecules. What you should be able to do is use these definitions up here at the top to identify what's the acid and what's the base. So all you really need to do is, you've only got two species here, so you just pick a species, and say, okay, well, let's see what happens between here and here. If I look at this, right over here, it's got this proton that's bonded to it. But then when we come to the other side over here, we know that that's gone. It's essentially donated. It's a proton donor. It's donated its proton. And where is it donated its proton to? It probably helps to draw this out a little bit differently. It's donated its proton to the ammonia that we had on the left-hand side of the equation. So this would be our acid. and this would be our base. So you'll note I've got my proton. Here I have a lone pair. Typically you have a lone pair in your base. Here that proton's been lost, and over here the proton has been picked up by the ammonia. So this had 3 protons on it, and now it has 4 protons. The base doesn't necessarily have to start with protons, but it should have 1 on the other side. So then we have these other definitions here. Just to make things more confusing. What we call this is the conjugate base. We'll call this the conjugate acid. And the reason is that if you were to run the reaction in reverse, this reaction is not, well, it's reversible in the sense that all reactions are reversible, but it mostly runs in the forward direction. It has an equilibrium constant that is very large. But if you were to run the reaction in reverse, then you can kind of see that things behave like, I guess then you see that, like, by our definition of proton donor and proton acceptor, so let me go ahead and write it in reverse. So all I've done here is I'm just flipping the reaction around since it's reversible. Actually, I think that probably makes things more confusing. I guess just imagine that the thing is running backwards. So if I'm running it backwards, what I'll notice is here I've got chloride, but then when I go to the other side of the reaction, the chloride has picked up a proton. Right, so if I run the reaction in reverse, this is now behaving as a base. And the same thing is true here. Here I've got a proton on the NH3, so it's NH4 plus. It should have a plus on it. So it's NH4 plus. But if I run it in reverse, now it's lost that proton, so it becomes the proton donor. So that's where the term conjugate acid, conjugate base comes from. So every acid has a conjugate base once it reacts, because now it's lost a proton, now it can accept a proton on the other side, etc. So familiarize yourself with those terms. Strictly from like a practical problem solving perspective, the conjugate base is whatever has lost a proton, and the conjugate acid is whatever the base was plus a proton. And then we have some other definitions that we can look at as well. So Lewis acid, well, so another way, let's say, to define acids and bases. So this top part is primarily where we'll be working, but we can work with Lewis acids and bases too. It's not a they're not mutually exclusive. They're the same thing. It's just a different way of defining things. So for Lewis acids, the acid is an electron acceptor. And the base is an electron donor. And you can see even in our previous example that the even by this definition, we would still correctly identify everything as in the same like acid-base context. We're just using a different. I guess, metric to measure it or define it. So for Lewis acid stuff, it's easier just to start with the base. So you'll notice here we have this lone pair, which I've explicitly drawn. And over here, that lone pair is now involved in a bond. So the electrons on ammonia, NH3, have been donated to the proton. So these electrons, I'm going to draw it explicitly with an arrow. These electrons come out and they react or donate to the proton on HCl. So this behaves as an acceptor of electrons and ends up going with the ammonia. So the place where this comes in handy, the Lewis. So these are Lewis. This is the Lewis definition. The place where this comes in handy is that you can look at things that don't have. So the Bronsted reactions or Bronsted acids and bases generally work well in water, but if you're working in a different solvent, like in organic chemistry or something, you're working in like chloroform or something, and you still want to think about things in terms of acids and bases, you can have reactions that proceed that don't actually involve protons. I'm trying to think of a good one. So yeah, I mean, so I guess it's hard to say where to draw the line, but like, so if you have, let's say, I might get a note somewhere where I get confused about what the actual mechanism is, but if you have boric acid, I guess it's a bad example because you're in, let's say, you're still in water. I'll use a traditional. Let's say you've got aluminum trichloride. Yeah, let's just say you have aluminum trichloride, and you're reacting it with another chloride. Sorry, the other example I was drawing was just getting too complicated. So in this reaction here, we don't have any protons. You don't have H+, which is traditionally what we talk about when we talk about acids. But we can still talk about it in terms of acid-base chemistry. In this reaction, the chloride would be behaving as an electron donor. Let's just mark the whole thing here. And it would donate its electrons to the aluminum to form a bond. So this would be our base, and this would be our acid. And so this site on the aluminum right here can accept electrons, and it accepts them from chloride to form this adduct on the other side. So electron donor. So identifying acids and bases, just by looking at them and identifying acid-base strength and stuff can be a little bit tricky. And you'll sort of build up an intuition as we go through the chapter. Mostly what we're going to be looking at, so aside from maybe like one question that's asking you about, is this which in this particular reaction, which one's a Lewis acid, which one's a Lewis base? We're not going to be working a ton with these, so I wouldn't worry too much about it. Yeah, I guess last. I don't know what this guy, Arhenius, there's too many damn definitions for acids and bases. There's another definition, another one called the Arhenius definition. For Arhenius, this really restricts you to water. So I guess there you're like, I guess in that case, you're always, I'm trying to think of like where people use the Arhenius definition. I guess it'd be like if you take a molecule like HCl and you put it in water, you get this out of it. Whereas if you take ammonia and you put it in water, you get this out of it. So by Arhenius's definition, this would be a base because when I put it in water, it produces hydroxide, and this would be an acid because when I put it in water, it produces H3O+. But again, and we're going to kind of see, I don't know why Arrhenius, like what context the Arrhenius equation comes up aside from this exact example I'm showing you. And you can see that even in the Arrhenius definition, you could still use the Bronsted-Lowry definition and still come out with the right answer. So it's like the Arrhenius is like the least general form. The Lewis acid definition is probably like the most generous form of trying to define acids and bases because it doesn't even depend on having protons. Yeah, there would be conjugate acids and conjugate bases. So somebody asks, is there a conjugate acid, conjugate base? So anytime you have a base or an acid, you can call the Lewis acid one maybe is an exception to this. But anytime you have an acid and a base, you can define, I guess one thing that's interesting about this example is that, well, so first of all, your conjugate base would be this. And here your conjugate acid would be this. And if I'm being better about my arrows, I would draw them in both directions. But sort of the neat thing about this one example is that it sort of demonstrates something that I think can be confusing, which is that acids and bases, it's a relative scale. So traditionally, we define things, we split things up and saying like, well, hydrochloric acid is an acid. But if you had, so you could create a situation in which hydrochloric acid acted as a base. it would take a lot of work, but you could, or a really, really strong acid, but you could do it. More commonly though, there are things that are like not strong acids or strong bases. And water is a really good example of that. So you'll notice in this top example, if we're looking at this from like where we're going to look at things in general through this Bronsted lens. If we look at the top example here, HCl is behaving as an acid, but water is behaving as a base, right? And so this would be our conjugate acid for water. But yeah, here, water is a base, and this is an acid. But if I change the context of the reaction, so I change what I'm adding to water, now here, water is acting as a base. I'm sorry, water is acting as an acid. So, you know, what about lysergic acid asking for a friend? We can talk about lysergic acid, but so water though, or like what you're looking at, I guess, like whether something's behaving as an acid or a base is dependent on what it's reacting with. So like, is water an acid or a base? Well, it's not, it can be either one, right? It can be a base in the sense that it could pick up a proton from HCl, or it could be an acid if you put it in the right, with the right chemical, because here it's donating a proton to ammonia. Yeah, lysergic acid, the like interesting properties of it, the psychedelic properties of it, don't really have that much to do with the fact that it's an acid. Although I guess its street name is acid as well. So we don't actually, there's no real interesting acid-base chemistry with lysergic acid. So sorry, there isn't a lot to talk about that. If you take organic chemistry with me next semester, bring it up again there and we can talk about it. Are there conjugate acid bases for the earlier example? Yeah, you know, I'm not sure. So I don't really think about Lewis acids and bases that much. Yeah, what would we call, like if we were gonna, the question is, are there conjugate acid bases for this example? I don't think so. I guess I'll make you a deal. I won't ask you about it on an exam. Yeah, I guess not really, right? Because we form this singular adduct from this. So this would be sort of like the conjugate acid and base sort of in one. Yeah. So for Lewis acids, maybe you don't have to worry about conjugate acid base as much. Yeah, so this is somebody else's question. What does a conjugate acid base mean over just acid base? It's just it doesn't mean anything different in the sense that like the conjugate acid is really just an acid. Like if we come back up and look at this more canonical example. So if we take this base, its conjugate acid is this thing with the proton on it. This is still really just an acid, right? The term conjugate just stems from, it just tells you its relationship to what the reactant was. That's really all it is. So over here we had a base. If you have an acid-base reaction, the base is going to always pick up a proton, at least if we're doing some sort of Bronsted stuff. And then, so you know that on the other side of the chemical equation, it's going to form a conjugate acid. And the reason that we have these special names for them, even though it is, again, it's just an acid because now it's a proton donor, is that there's a relationship thermodynamically between the base and the conjugate acid in terms of their strength. And we'll get into that when we get into, I don't think that was in the LE. We'll get into that when we get into, and we can maybe even get into that today. Yeah, well, I guess we have to get into Equilibria before we can talk about that. So yeah, so there's a relationship. There's a relationship between this and this. Those things are tied together through thermodynamics. So they're tied together through an equilibrium constant. And so by using the term conjugate acid, it just helps us kind of track what we're talking about. Although I agree with you, or I don't know if this is exactly what you're saying, but it's confusing. Acid-base, conjugate acid. If you go and take OChem, we do a chapter on acid-base chemistry, so it pops up again. A lot of this stuff that you learn in Gen Chem won't pop up again in most of it, ever again. Ever again, is that true? Some of this stuff I've never used in my entire career as a chemist, but it probably just depends on where you specialize. Acid-base chemistry, though, is, of all the things that you can learn in general chemistry, is probably one of the most, I don't know, it tends to show up in a lot of different places in chemistry. Like if you're looking at biochemistry, or biochemistry is a good one. Acid-base chemistry is super important. Organic chemistry, acid-base chemistry is super important. Most reactions tend to require a little bit of acid or base to get going. So like your blood has a pH associated with it of, I think it's 7.4, and it's got a buffer and all this kind of stuff. So there's a whole bunch of stuff that happens in the body that's very dependent on acid and base chemistry. Okay, so it's also, I think one of the things I like about this section, even though it does get a little bit, we kind of get down in the weeds with solving problems and stuff, which I know can be challenging, is that, we're actually talking about chemical reactions here, and not just like, I don't know, heating a glass of water or whatever, like we did with the last chapter. So it's nice to be able to do some stuff with molecules, since it is a chemistry course after all. Okay, so primarily, so most of the time, so acid-base chemistry has context in any solvent. You can talk about the pH of something even if it's outside of water. We mostly focus on water because, water is the most common solvent on our planet, and all biochemistry takes place in water. So understanding how acids and bases work in water is, that's sort of the one of the key things to understand. To understand all these other different types of phenomena like ocean chemistry, and why like I don't know, people who think that not that if you think this, I'm not trying to give you a hard time, but like why people think that eating foods that are acidic, or there's like this sort of like weird thing on the internet about like blood alkalinity or alkaline foods and stuff. That's not really true. Or there's not a lot of truth to it, at least. So I don't know, acid-base chemistry in water is important. But yeah, so the water is sort of a weird. So I kind of hinted at this in the last thing that we talked about. So one thing I guess that I would be able to do, just based on what we just did, since this is try to make these sort of problem solving oriented, but since we just had an exam, I didn't want to overload you guys with stuff to learn. Is be able to, for a particular reaction, you should be able to identify the acid, the base, the conjugate base, and the conjugate acid. Yeah, that's what I would do. I'm sure we have some problems somewhere in the massive amount of problem. Isn't drinking a special pH water good? I don't think so. I mean, I just drink normal water. Like this water is straight out of the tap. I mean, maybe if you're drinking alkaline water or something, you've got some sort of esophageal like acid reflux thing. It might help a little bit, but We actually took, one of my friends when we were in grad school took some alkaline water from somewhere and we measured the pH of it, and it was just normal pH water. So I think sometimes it's just, they're just lying on the bottle. If you want to, you can just take antacids. If you're drinking alkaline water, just take some Tums or something, you'll be fine. When we get to buffers, we'll talk about this more, but most of the things in your body are buffered. So small changes in pH are just kind of inconsequential. Certainly your blood never changes its pH. If it did, you'd be dead. It's very, very like strictly buffered at 7.4. If you enjoy drinking alkaline water, you go for it and you drink it. But does it have any real health benefit? Probably not. Well, I would say almost definitely not. Yeah, we'll do lectures on YouTube, I think. I'm trying to figure out exactly which lectures to put on there. But we're just getting kind of warmed up into the new unit here, instead of kind of, just because we just had an exam, I thought the people might not want to watch lectures before class today over the weekend. So I figure we just kind of dip our toe into this material slowly. I'll try and cut down on the content in the lectures. I don't know, I feel like yeah, maybe we could switch I was thinking it might be a good idea to flip the YouTube videos to just be more problem solving and flip this to be more lecture oriented. Yeah, I think that might be good. Okay, good. I'm getting a lot of support for that. Let's see. All right, so yeah, the online course format is kind of throwing me just because I'm not used to it, and I'm not totally sure what the best way to do it is. But yeah, so water does this autoionization thing. Yeah, I guess I'll do that. Let's just do that, since I got at least who's in class right now seems to be more interested in having the problems be the YouTube videos be problem solving. One of the problems I have with making like the YouTube lecture videos is like there's something about not having a class that just makes everything just feels so much. But like even when I'm talking, like God, this is like there's like no break in the information. Like people don't ask questions. There's no like everything just feels a lot more boring. It's like hard to be remotely entertaining making videos. And I imagine watching them is just super dry. So. But all right, so in the next part here, we're looking at this reaction, which I kind of hinted at when I talked about acid, water being both an acid and a base. So if you just have a glass of water, water is mostly in this form of that we're familiar with, which is HOH. Yeah, let me write it out. You know, where you've got it all bonded up together, but a very, very small concentration of this will form H3O plus and OH minus. So what's happening is the water is essentially reacting with itself. So the electrons on one oxygen atom are going out and stealing the electrons, or stealing a proton from another water molecule. And so you're ending up with You're forming a little bit of acid, or I guess technically speaking, this would be the conjugate acid. But you're forming H3O plus over here, and you're forming a little bit of OH minus. Yeah, so we call this autoionization of water. The concentrations of these things are very, 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 very low. Specifically, you come out with 1 × 10⁻⁷ molar of each of these. So remember, I know the scientific notation stuff all these numbers start to look the same, but you'd end up with 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Yeah. So, you're talking about a concentration in water of 0.00001 molar of H3O plus and of OH minus. So there's not a whole lot of this around in water, which is why generally when we talk about water, we just talk about it as being H2O. But we can define a value for this. We call it Kw. So remember that when we're writing out our equilibrium constants, we didn't harp on this too much, but if something's a liquid or a solid, it doesn't enter into our expression for the equilibrium constant. So what would K be for this thing? K would equal the products over the reactants, but the reactants are all liquid, so they don't even enter in. So it would just be H3O plus times OH minus. And we give this a special little subscript on there, which is W. Yeah, H3O plus is called hydronium. And if we want to use the other name, this is called hydroxide. Let's see. So Kw is going to be equal to H3O plus times OH minus, or hydronium times hydroxide if you prefer. I tend to just say out with the products are all aqueous. That's right. You'll note that these are aqueous. And so these actually enter into our expression over here for the equilibrium constant. So, so we can calculate Kw for this, and we'll see that this comes in handy. Kw is just going to be then equal to 1 × 10⁻⁷ times 1 × 10⁻⁷. Which will just be 1 × 10⁻⁴. And so what we'll see though is that OH minus and H plus are tied together through this equation. And if you know one, you essentially always know the other one. Yeah, so what's that? So I guess just to kind of, like if you fudge the pH a little bit. So like, let's say, so this is for pure liquid water. If I add HCl or something to this, now I'm going to form more hydronium. This is where the Arhenius kind of thinking comes in, but I'll form more hydronium, but Kw still has to equal 1 × 10⁻⁴. And so if your H3O plus concentration goes up, then that means that your OH minus concentration must go down, because this always has to hold, which gets back to kind of what we were talking about with terms of equilibrium. Yeah, the Kw just means water. It's the autoionization constant for water. It's just like a special one. Sometimes you'll see, like for acid, what we'll talk about, it'll have like Ka. written on the bottom. So we have like special subscripts that we put on those sometimes, but they always generally or almost always mean the same thing. It's always the mass action expression that we learned in the last unit. So not a dumb question. Why wasn't H2O in the denominator of KW? So if you have something that's a liquid or a solid, it doesn't enter into the mass action expression. And so water is a liquid, so it doesn't enter in. So gases and aqueous components enter into whatever the K expression is, but liquids and solids mostly do not enter into it. And we'll talk about solids when we get to KSP, which is a measure of solubility. Okay. Yep. So we'll finish. I really like to, maybe I can get into acid-base equilibria. So really quick, well, so if we're looking at water, this is just, I'm just following what the GChem website is saying here. If you have more H3O plus than you have OH minus, you've got a solution that's acidic. And if they're equal, that means you've got a neutral solution. So the main thing to take away here that's hard to see without actually working through a problem, though, is that if you know H3O plus, then you necessarily know OH minus. So if we know that KW is equal to this, so like let's say that I know the H3O plus concentration in solution. Since this is a constant, so this is one that you could commit to memory, since it's 1 times 10 to the 14th, I necessarily know OH minus. So I can always calculate, let's say OH minus. Let's say I know what the H3O plus concentration is. Then I know that, then I can immediately calculate OH minus. And the same is true if I know H3O plus. I'm sorry, if I know the OH minus concentration, then again, I know that I can just solve by doing this. But the thing that's crucial, I guess, or sort of like the linchpin for understanding all this stuff is that H3O plus and OH minus are like always tied together through KW. So if I increase H3O plus, this is kind of gets almost to it just sort of ties back into what we talked about with equilibria, which is that if I change the concentration of one of these things, like let's say I just dump a whole bunch of hydroxide in a solution, the hydroxide concentration is going to get larger. I know it's hard to kind of, the way that I explain this, it just, every time I say it, I know it's kind of hard, but if KW is a constant, and I take on the right-hand side over here, and I make one of these numbers larger, so like let's take a OH minus and I'm increasing it. Because this number can't change because it's an equilibrium constant, that means that something over here is gonna have to give. So if this number is getting really, really large, that means that H3O plus is going to have to be getting really, really small. And this should be sort of intuitive because acids and bases work in opposition to one another. It's kind of like hot and cold. Like you can't have, at least not for very long, right? Like you can't have two things. You can't have something that's both simultaneously hot and cold. You know, like if I put ice cubes into a cup of hot coffee, what ends up happening is they come to some sort of equilibrium, right? The coffee cools off and the ice heats up. And acids and bases are just like that. Like you can't have both of them simultaneously. If I take an acid and I put it with a base, they're going to react to one another and become neutral, right? So if I dump a bunch of hydroxide in the solution, then I expect that there's not going to be any acid present. The hydroxide is going to chew up all the acid. Just like if I take a cup of coffee and I just keep dumping ice into it, the hot cup of coffee is just going to eventually just become completely cold. So they decrease, they're sort of opposites in the same sense as hot and cold are opposites. So both will not be present at the same time. And Kw just gives us a mathematical relationship between that, which is to say that if I increase the concentration of OH minus, then H3O plus must go down. And the same is true. If I increase the concentration of H3O plus, then the concentration of OH minus must go down. So that's what Kw allows us to do. Okay, so reasonably soft introduction to acid-base chemistry. We'll pick up on Wednesday. Let's see. So we'll pick up on Wednesday. We'll talk about strong acids and bases quickly. I think you guys have seen some of this stuff, hopefully in another course. And then Kw is a constant at constant temperature, like all equilibrium constants. But yeah, we'll talk quickly about strong acids and strong bases, and then we'll move into what is the more difficult type stuff, which is acid-base equilibria, and then ultimately into titrations and buffers and stuff, which is really the stuff that starts to give people, I don't know, problems. So get some of this basic stuff down. Look over, pay particular attention to the Bronsted definition. And then, yeah, let's pick up on Wednesday. And I'll try and I'll think about what some good problems are to put up on YouTube for you guys. Yeah, and that's it. I'll take a quick break and then I'll be in office hours. So I'll see you guys again soon, or some of you guys. Yeah, thank you guys.
Hi guys, did he mention anything about the test? I just missed the first few minutes this morning, so do y'all know?
No, I didn't hear him mention anything.
Okay, thank you.
Oh,
I'm going to mute all you guys, but feel free to unmute yourself.
can I ask the problem of the exam?
Okay. Let me mute everybody just so that it like zeroes everything out so we can get rid of the background noise. And then if you unmute, if you want to ask me a question, you can also ask in the chat window, but then just unmute yourself. But that at least gets rid of anybody who accidentally left their mic on. Okay. I don't think we have time to go over all of the 25 questions in the exam, but yeah, we can certainly, I figured you guys would want to go over the test right now. So all right, yeah, go ahead, shoot whatever questions you guys want to look at, we can look at. Okay, so I got number one. Let me get a list here. We got 23. Any other problems you guys want to take a look at? There's 22 people in here, so we have time, isn't it? Yeah, 21. I'll see how many I can get to. If I can't knock them out, we can either knock them out on Wednesday or I think Ryan has office hours today. Ryan will know how to work all these problems as well. I can't open the exam page. Yeah, we closed it because some people had to take it later. Let me see real quick if I can turn some knobs on my end so that you guys can see it. Yeah, giving exams on, I don't know how many of you guys, this is your first semester at UT, but giving exams online is a little bit, I'm still trying to figure out like the best practices for this. I hate the, for the exam grades. Yeah, so the exam grades, so I feel bad, especially because I know that what the last day to drop is today, right? So on like Thursday, I went in and I was like looking through the exams and trying to figure out like where people like missed, you know, what problems people missed and trying to figure out if there were problems that were unfair or something. Canvas has a thing in there where you can like, I guess it's like a curving function. Like you can hit a button and it'll curve everybody's exams. And I was just trying to look at the average of the exam and somehow the curving thing got activated, which I'm aware of not to do. And then, but once it gets activated, there's no easy way to revert it back to the way it was. Like you can't just hit a button to undo it. And the way it records the gradebook history is it like I have a history of everybody's grades, but instead of giving that to me in a list, it gives it to me in like these very weird format that I can't copy and paste immediately back over. So I think what I'm going to have to do, even though I've reached out to the camp, free curve, but in the wrong direction, man, I'm sorry. It curved them down to like a 50 or a 60 for everybody. So I don't think that helped very many people. Maybe people who got like a 10 or something in a test got bumped up. So anyway, so I think what I'm going to end up having to do is go in and manually re-enter everybody's grade, which is not a big deal, except that, you know, you guys can't look at your grades right now, but whatever grade you got out of the exam is pretty much your grade. Even if we curve them, which I don't think we will, it would only be like a couple of points or something, so it wouldn't be earth-shattering. Usually what I do for curving is just wait until the end of the class because we drop an exam. That way it's like, that way the curve sort of gets applied to the general grade. And so what am I trying to say? If I curve, like, let's say this exam by 2 points or something, and then this ends up being your drop exam, then it doesn't actually help you at all. Whereas if I just wait until the end and just curve everybody's grades at once, then it helps everybody sort of equally. So, and the grades were generally pretty good. So it, you know, I think there's, yeah, I prefer that too. But the grades were pretty good. you know, this is not a criticism of you guys, but I think the main problem that students have is just like not, because it's open book and stuff, is not preparing as well as they could. And so they're a little bit slow on solving problems. I know some students had trouble finishing the exam, but this exam, this exam was easily finished in 90 minutes if you know what you were doing. If you kind of knew what you were doing and trying to like, you know, look for problems that are similar online and in your book and stuff, which is fine. It's an open book exam. I think that's where some people ran into problems. So I think that I'm just going to have to emphasize that there needs to be a little more practice. The students that you guys just need to practice a little bit more. And I know it sucks right now. It's hard to keep up with things. We're all like kind of just shuttered inside. And I empathize with that. But we'll take a look at the end of the semester and try and figure out how to fix if there's any kind of fixing that we need to do to the grades to get you out of here. But anyway, so I was in the middle of doing, oh right, opening the exam back up. Yeah, I mean, I'll work practice problems in my office hours. Is there a desire? I guess I can sort of poll if there's a desire to do longer practice problem sessions. I could be persuaded to do that or try and get Ryan to help out with that as well. So for my organic chemistry class, 17 was another one. When I teach organic chemistry, which is you know, traditionally a really hard course for students. What I did last semester, although it was interrupted by the pandemic, was have Saturday morning, I would come in, I think it was in the morning, but it was a 6-hour session, I think, or maybe it was 11 to 6. And I would just sit in one of these big classrooms and students would kind of filter in and out and we would work practice problems. And that, I think it was effective. Students showed up at least for a couple of hours. It does start to wear on me just because 6 hours of talking. I love talking about chemistry, but just the 6 hours of talking, I just get personally exhausted, and then my voice and stuff starts to hurt after a while. But the nice thing about being able to do those long problem working sessions in person is that the students generally like work with one another and stuff, which I really like. And I don't know how to emulate that in Zoom very well. Maybe like breakout rooms or something. Everything's just such a big pain in the ass online. But yeah, if there's a desire for more problem working sessions, we can do that. And I can also make more YouTube videos that just like dig down on problems. I'm not a very in terms of instruction, I'm not like a super tidy, concise, to the point type teacher. I feel like there's two varieties of instructors. Like some people get really down into the details, and then other instructors are like very fast in terms of how they talk about stuff. And I tend to be more wordy and stuff, which is, I think, okay in person, but it doesn't translate super well into YouTube videos is what I've realized, because it's just like, they just go on for so long. And I know that without any kind of like interaction, that can be a little bit rough. So no, that's nice of you. Thank you, Frida. But yeah, so I don't know. We can put together some more practice problems sessions. I'm like really like, that's my thing is if you want to do well, you just got to work problems. And so I want to make sure you guys feel supported in that. So let me think about when I can do that. Everything's complicated over here just because we don't have any childcare or anything. So, and I also just personally enjoy spending time with my son. So, all right, I made a note. Let me think about it and think about when I have time to kind of do a problem solving session. I'll talk to Ryan and see what his situation is. And maybe I'll talk to Somolenko, the other instructor, and see if they have time as well. And we can kind of, yeah, problems on YouTube are helpful too, I think. All right, so we've got problem. Thank you guys for feedback and stuff. I appreciate that. I want to make sure that you guys are getting what you need. We got 1, 23, 21, and 17. Let's take a look-see. again. I need to reopen this. See, I want to reopen it, but I don't want you to be able to take. Okay, so I just have to change this, I think. I'm terrified to press the wrong damn button inside of Canvas and create some sort of nightmare for me. Canvas is not the worst software I've ever used. I think Quest, I don't know if any of you guys have experience with that. That's another thing that people use at UT, is the worst software, but it's pretty bad considering that their company's probably valued at like hundreds of millions of dollars. I'd expect better. It's bad on the back end that I work on, I think. All right. These guys, all these online learning platforms or learning management systems, if they're called, they're just making so much money right now during the pandemic, man. It's crazy. If you want to get into a racket, school software is a good way to go. Let's see. All right, so it should hopefully be available. Yeah. I'm like pretty used to Canvas because I've used it for like several years. It's just like, there's some features on there that it's like any software where it's like you want features that are, you want different features on the, it's the back end that bothers me. You want different features for like being able to manipulate grades and being able to upload stuff. And it's just like not very smooth, you know, like if I want to alter grades, you have to like export it to a Excel spreadsheet, do a bunch of changes in the Excel spreadsheet, and then like re-upload it, but it has to be re-uploaded in a very specific format. It's just like not a very smooth experience for, you know, for it being 2020. Like in 2000, I'd be like, this is amazing. But it like 20 years later, you know, now that we've had the internet for a while and most UIs are really simple to use, I'm like, this is bullshit. All right. So let me know if your exams are available. Still muted, son of a bitch. All right. This is another feature that sucks about Canvas. What I could do, what would be nice for me to be able to do, right, is to just be able to export a PDF of this and upload it. But there is no such feature. Why is there a curve that makes grades go down anyway? Yeah, I don't like curves. Usually when teachers talk about them, it's like, oh, we're curving the grades so that, you know, that improves everybody's grades. But realistically, what a curve is it sets the mean of the grades at a particular score and then forces all the other scores to be where that mean is. So one way that teachers do this, although this is really uncommon now, is to be like, well, the average for the class should be a grade of a C. And so they'll curve all the grades to where everything's a C. So even if you got a 95, it'll pull your grade down from a 95 so that the distribution is such that the average score in the class is a C. So a curve is really a statistical treatment of the grades. But I think it's kind of colloquially become like we're adding points to your grade. All right, hold on, let me see here. How do I make a I think I've turned all the knobs on my end that I know how to turn. I changed the availability date to December 31st, so you should be able to see it. Unless is it just not appearing at all? Maybe I don't have it published. Grades are muted. That's appropriate because they're still messed up and I haven't fixed them yet. But maybe because the grade is muted, you can't actually see the exam. I just want you to be able to see the exam questions themselves. I don't want you to be able to see your grades because the grades are not accurate right now. Can you see your exam questions at least? God damn it. All right, well, I don't want to spend all of office hours tinkering with that. Let's, let me see what I can do here. I'm sure there's some way to do it. Maybe because I think maybe because I have it muted, it won't let me, it won't let me show them to you. Yeah. I can copy them verbatim though, so that because if you have questions, like if you think there's a typo or something, that way we know. So let's just do it that way, and then eventually we'll make the damn exam available. There's a bunch of things I have to fix with this exam, like the curve, and then also it should be at 100 points, not 24 points. It's another nice thing that Canvas does. It won't let you just normalize the grades. Anyway, this isn't me just bitching about Canvas. I mostly just get aggravated because they charge the university money, which it does. At least it's not directly charged to you. You guys don't have to pay an additional $50 or something to use Canvas directly. I don't think, at least. But you know, it is money that gets taken away from the instructional budget. All right, water gas shift reaction. Let's look at this first one. Okay. Yeah, I'll figure out how to make the exam show all of this stuff. And normally it shows you afterwards, like for example with the LEs, it lets you see them later. I'm wondering if because I have it muted, it's the grade's muted, it's not letting you see them. All right, so the first problem is let's see. It says the water gas shift reaction below is an important industrial process for the production of various petrochemicals. Clearly not going to be super relevant. Use this equation for questions 1 through 3. How will the following changes affect equilibrium? And then the first one is adding CO gas to the reaction. 2 is heating the reaction. 3, increasing the pressure. All right. This. So our reaction that we're looking at is carbon monoxide, a gas, and then we've got steam, which is also a gas. And then we know that the delta H for the reaction is equal to minus 41 kilojoules per mole. Yeah, so adding carbon monoxide to this should shift the reaction. So for part one, so if we add carbon monoxide, that's going to shift to the right or to the products. I don't know how it's worded in the answer choices. Heating the reaction, because it's negative, that means the heat, you can write it out as being kind of over here. It's going to shift left. And then increasing the pressure should have no effect on the reaction because the number of moles on the left and right are the same. So that's generally, so this one is, so remember for increasing pressure or changing the pressure, that shifts the reaction to the side that has more moles because there's 2 moles on the left and 2 moles on the right. There is no change from increasing the pressure. And then heating the reaction is just a matter of knowing if it's exo or endothermic. And then yeah, adding carbon monoxide is that's one of the more straightforward ones. If you add something to the left, it's going to have to shift over to the right. So that's that one. That one's Le Chatelier's principle. Number one, a mystery salt. Let's see, 23. So we'll go to 17. I'll just go in order here. Oh, you know what I can do? Well, I can't share both. Well, actually, what can I do here? Actually, got to be careful with let me see if I can share my desktop. But I can't see. Well, actually, I can bring up my. This will get a little messy. Nope, we don't want to see me in multiple different ways. There we go. Okay, good. I got some follow-up questions on that. This allows you to see the exam and the screen, hopefully the same. Yeah, heat in the products means it's exothermic, so you can kind of think about it as like, yeah, heat is literally, well, I don't know about literally, but it is a product of the reaction. It's like burning something, you know, heat comes off of it. So you can think of it being on the product side of things. It's not strictly true as far as like why that causes the reaction to shift back to the left. That actually falls out of some other equations, but like it's a useful way to think about it. Okay, so yeah, so problem 17, if delta H is negative and delta S is negative, what will happen at low temperatures? And then they give you some answer choices. If delta H is negative and delta S is negative, what will happen? Oh, so like, what's going on in this question here? So they're telling us that delta H is negative and delta S is negative. Yeah, so what it's getting at here is that if delta S is negative, I don't know about this small, I don't like that language very much, but S is negative. Huh. I don't know. What? Yeah, this is just kind of confusing. Let's see. Low temperatures. Reaction proceeds spontaneously because T delta S is small. Oh, low temperatures though. It does say low temperatures. Okay, so that's an important part. Okay. Sorry, I thought it didn't say I didn't see the temperature part. Yeah. So it's saying delta H is negative. Delta S is negative. So but then it also says it's that temperature is low. And so, it's qualitative, so it's not saying exactly how low, but in terms of just picking from multiple choice, what's the most correct answer here? It's that the reaction is going to proceed. So for low temperature, so you can imagine in the extreme case, if delta S at the extreme end where like the temperature is close to absolute zero, then the T delta S term just gets really, really small. And so this part here, which is a positive number, the magnitude small at low temps. And so you expect, so delta H dominates at low temperatures. Let's see what you guys are saying here. Yeah, the small versus large part. So small and large generally, I can see why that's confusing. Small and large, usually when you're talking in like especially in like a physics class or something, generally refers to the magnitude, not whether it's negative. So like -10 or like -100, the sign on that isn't related to the small part. The small part is the number itself. So like -1000 is larger. Yeah, okay, I can see how this is confusing. Like, because it's larger, but like it's not greater than 1000. I get it. I'll put a note here. Let me think about it. So yeah, so it does mean magnitude. It does mean magnitude. So you're thinking in the right terms. But T delta S is going to be small because you're at a low temperature. So if you think about the extreme case of being near zero, so you get things to absolute zero, you're in like outer space, that T delta S term falls away. So the entropy for like, when you're looking at what this equation tells us, one way to read this equation is that the enthalpy of something, this term, isn't particularly temperature dependent. But the entropy term, which I outline in red here, is extremely temperature dependent. So for systems where entropy dominate, it's typically when temperature is really high. Yeah, so you can't okay, yeah, I see where the confusion is. So this temperature is in Kelvin, which runs from absolute zero to infinity. So it doesn't have negative numbers. So for let me think if this is true. For thermo, it gets confusing because sometimes we do actually use Celsius. But for these delta G, delta H, and delta S, especially for delta S, usually we're referring to temperature in terms of Kelvin. Certainly for this equation, it's always in Kelvin. That's why, like, when we say, yeah, you don't just, well, yeah, you assume, yeah, I guess you could say you assume, but just like for that particular equation, the temperature has to be in Kelvin. For other things, like when you're dealing with, like when we deal with heat capacity and stuff, you can use degrees Celsius. But for this stuff, you have to use Kelvin. And this is because we use Kelvin, it sort of gets at this thing where you can say like spontaneous at all temperatures or non-spontaneous at all temperatures. So if delta S is negative, then the entropy term never ever becomes like a contribution to making the free energy negative because of that. Yeah, it's not like I don't know. It's not a perfectly worded question, but I think it's okay. I think it's okay the way it stands. Okay, so that's 17. Let me see my other ones we had here were 21. No, this is the unknown salt one you guys were talking about. Yeah, this is a reasonably hard question. So we've got 3.3 grams of an unknown salt. It's in 300 milliliters of solution. Hopefully this is an osmotic pressure problem. Oh no, temperature solution climb from, oh, okay, it's a heat. The solution is the same for pure water. What is the identity of the salt? So yeah, so this is like one of those molecular weight problems like we worked on, but just in like a different form. So we worked a couple of problems where you looked at the osmotic pressure and you use that to calculate the molecular weight. Let's see what your choices are. Yeah, so they give you the molecular weights here. Yeah, so all you're really trying to do here is find the molecular weight. Temperature of the solution climbed from 25 to 40. Delta H solution is calculated to be minus 300. Assume the heat capacity and density. Delta H. Assuming the heat capacity and density, what is the identity of the salt? So we've got delta T. Let's see, and then we have delta H solution. Heat capacity and density of the solution are the same for pure water. Lots of information here. And then obviously, density maybe. Just didn't know what equation to use because Van Hoff, K constants, or osmotic pressure wouldn't really apply. Yeah, Ian, how did you solve this problem? MCAT. Excellent. This is like I wish we had the volume on. All right, so Ian started with the heat equation, M equals C sub P delta T, which is a reasonable place to start, right? Because we have the heat capacity, we have a change in temperature, and it tells you the mass. How did you go from that to, so what do we need? So anytime you're trying to figure out the molecular mass for something, all you're really trying to push towards, if you know how much you started with gram-wise, is the number of moles. So how did we go from the heat equation then to moles? That question, does that answer? Yeah, divide by the H solution by heat, yep. This question's a little bit hard, but yeah, so you can see moles appears here. So the way the experimental setup is saying is like, if I take I don't know why it works mathematically. It seems to work very good, Ian. I feel like I feel like I got through at least a couple of exams in undergrad, just plugging in numbers and getting until I got to the units I needed. But okay, so what this is saying is, I took 3.3 grams, I put it in the water. So I've got like some salt. I don't know what it is though. Let's call it XY. We'll just call it X. And I dissolve it into water. And so now X is dissolved in here. What I see is heat flows out of the system. So I get some Q off of that. That's what this number is here. Right, so Q flows out of the system. So I have minus 320.2 kilojoules. Well, let's say that would be for a full mole. Yeah, so let's just leave it at that. So Q flows out of the system. Some amount of heat flows out of the system. Actually, per mole, though, it's kind of an interesting. Assuming the heat capacity and density of the solution. We'll have to think about that. So yeah, okay. I think I see how to do it. Okay, so you got So I think I see how to explain it at least. The Q is equal to, so we can calculate Q using this equation. Times delta T, which is 40 minus 25. So at least they were nice and our units all work out. So 207 joules flows out, assuming I punched that in my calculator right. And then delta H is solution. For whatever that means whatever amount of salt that's being dissolved is going to be equal to minus 320 kilojoules. Climbed, yeah, 40. Okay, so you know it heated up. So this makes sense. Okay, so we could put a negative sign on that if we wanted to. Per mole. And then now it's just to say, so since all we're ever pushing for when we're trying to figure out the molecular weight for something is moles, we know that if whatever this compound is pushes out minus 320 kilojoules of heat for 1 mole. That if it pushes out 207 joules or 0.207 kilojoules, that's going to be equal to whatever the number of moles is that's been dissolved. So we can solve for that. What did I do wrong? Oh no, that's the number of moles. Okay, we're good. That's a negative number. Oh, because I put in a negative number. Now I'm still good. And so we know we have, I feel like I must have made a calculation area somewhere, but we'll see. So if this is the number of moles, this tells us the number of moles that must have been dissolved. And since we know we started out with 3.3 grams, that means you have 3.3 grams per 6 times 10 to the minus 4 mole. That seems like it's going to be a grotesquely large number. I came up with some crazy large number. Hold on, I made a calculation error somewhere. Oh, I used 3. Oh. Wait. Yeah, I'm a. Okay, that explains the problem. Yeah, the amount of heat that comes off is not related to the heat change is not the number of grams of salt; it's the number of grams of solution. Yeah. Okay. Now we get a more reasonable answer. So then we come out with 18,000 joules. which is 18.28 kilojoules. That corrects that error. Okay, so now we've got our moles. Yeah, because you're given the density of water, or it says it's the same as the density of water. So that's how you know that the number of grams. Okay, yeah, now I got a good answer. The last answer I came out was like 56 trillion or something. So we come out with 56.1 grams per mole, which is reasonable for a molecule. If we come down, yeah, it's KOH. All right, yeah, so from the top, you're given all this information here. Anytime where you, here they're kind of wording it, here it's kind of worded in a way that's a little bit like cloudier, I think, than some of the other ones, but it's, anytime you're ultimately trying to figure out the molecular weight and you're given the mass of something, what you're really trying to figure out is the number of moles, and then you're going to take the number of moles of that substance and divide it by the number of grams that you started with. So it says the temperature of the solution climbed from 25 degrees Celsius to 40 degrees Celsius. The delta H solution, which is how we're going to get our moles, is some number, and then it tells us the heat capacity or whatever. So the trick is, using this equation that we know that for some change in temperature for a solution, we can take it and multiply times the heat capacity and the mass of the solution. That was the error I made. It was excellent calling the mass of the salt. We take the mass of the solution, we can calculate what Q is. So the mass of the solution here comes from this. In the bottom of the question over here, they're saying, assume that the density of solution is the same as pure water. So we know it's 1 gram per milliliter. So if I've got 300 milliliters, I have 300 grams. That's how we know to put in 300 grams there. And that gives us this number. So that tells us the amount of heat that comes off the solution when we dissolve in 3.3 grams. And since we know that delta H of solution, which is the heat associated with the delta H of solution, is the heat that comes off of the solution. So that's evolved off of the solution if I dissolve a full mole of whatever the salt is, which we don't know yet. And so that's where this calculation down here comes in. So this tells me that it's saying, well, I know if I took a mole and dissolved it and measured the amount of heat that came off, I would get 320 kilojoules. What I actually see when I dissolve in 3.3 grams is that I get 18.8 kilojoules, or about 19,000 joules, but I get 18.8 kilojoules. So this is what I see when I do a mole. This is what I see when I dissolve in 3.3 grams. But because I know this number and this number, I can use that to calculate the number of moles there. So I know if 320 kilojoules evolves when I dissolve 1 mole, I can say, well, how much, if 18.8 kilojoules evolves, how many moles must that take? And that allows me to calculate this out. And then I just take that number and say, well, if I know if I know the amount of moles that were dissolved in here was 5.8 times 10 to the minus 2, then I know that, and I know that I dissolved 3.3 grams. That means that I have 3.3 grams per 5.8 times 10 to the minus 2 moles. And that allows me to get the molecular weight. I roll down the screen. I think I already rolled down the screen. I roll up. Which way do you want me to go? And on which screen? Sorry, I got a lot of screens open here. Anyway, yeah, this question's a little bit challenging. Make the screen bigger. Yeah, that one was a little tough. That's probably one of the harder problems on the exam, but yeah, ultimately when you're trying to figure out the molecular weight, you're trying to figure out the number of moles. I think the key thing is here is understanding what, I'm not sure what part bottleneck for people, but the delta H solution thing, recognizing that delta H solution tells you is related to what the amount of heat that you're going to feel that comes off as you, or is related to this QMCAT equation is probably the key thing there. I think that's the biggest I can make the screen and have them both up on there. Unless I can shrink the canvas screen more. Yeah, I can do that. There we go. Okay, so that's 21. I can hang out and do, I think we have one more problem. 23. Oh yeah, okay, this is more straightforward. Okay, yeah, see you later, you're welcome. So this question is just which salt, when dissolved in water, will have the lowest freezing point? And it gives you a bunch of different options here. This is just a, this is just an application. Two possible answers. It's, yeah, maybe it has two possible answers. Let's take a look at it. I feel reasonably confident in the test questions. I didn't have time to go over it because I was doing some childcare stuff, but I know Ryan made it, and then Dr. Samoilenko went through it pretty carefully. So it was proofread pretty well. Which salt dissolved in water will have the lowest freezing point, but that doesn't mean we don't make mistakes. So, I mean, the trick here is you just want to look at, I mean, there's a lot of ways to look at this, but one way to do it, this is maybe a longer way. As you look at what practically you're going to end up with over here. And then we can say, let's see, so for this first one, you start with 0.11, 0.10, 0.09, 0.12, and 0.16. So you're looking at like the Van Hoff factor or whatever for each of these. So practically your practical concentration here is going to be 0.11 plus 3 times 0.11. And the practical concentration here is going to be 0.10 plus 2 times 0.10. This will be 3 times 0.9 plus 0.09, 2 times 0.12, and 0.12, and then 0.16 and 0.16. I don't know, in my mind, like I'm always drawn to the ones that have the largest Van Hoff factors, which is sodium phosphate and iron chloride at the top. It looks like iron chloride turns out to be the correct answer. But yeah, if you just go through and calculate it for all of them, there's probably a way to eliminate some of them without having to do the calculation. But so this is 0.44. I don't know if the M is molal or molarity, but that's the practical concentration of that. Oh, did I mess up here? Hold on. Yeah, so you end up, having this is how I would work through it. So, I mean, I guess I'm trying to think of like, yeah, I guess you're just trying to calculate, I guess the easier way to do it is like, yeah, if you can say like I equals 4 for this, I equals 3 for this, I equals 4 for this, I equals 3, and I equals 2. And then you could just, that's probably the easier way to do this, is just multiply. Then you could just multiply it times that number. So you're like, okay, that one's 44, this one's 30, this one's 36, yeah. But yeah, getting the Van Hoff factor is the main thing. I don't know exactly what your issue was, but like, I feel like one issue for students is, I just derped out, that definitely happens. Yeah, sometimes students will get confused with the polyatomic anions and not know how to break those up. But if you've got those, it shouldn't be too bad. Yeah, it's easy to screw up and just make typos and stuff. And that's one of the shitty things about multiple choice tests is like, you know, like just making like basically know what you're doing and just making like a minor error gives you the same amount of credit as somebody who has no idea and just guesses. But it's just sort of the general situation that you find yourself in, especially at a big university, especially for online tests. So, anyway, all right. Well, that nicely wraps up office hours. That's the last problem you guys asked for. Yeah. All right. So on Wednesday, we'll pick up in office hours. I mean, if you guys have more questions about exams, we can work on more exam questions, but more than likely we'll move on to doing some acid-base chemistry stuff. I'll try and have a good list of problems for us to work on. Yeah, you're welcome. And yeah, I'll try to get some problems up on YouTube and some problem sets to try and help keep pacing for the acid-base stuff, so you kind of know that you're on track to do well in the exam. But all right, thanks guys.
Have a good day.
Yeah, you too. Thank you.